Huh?
You're just chilling.
I'll be in the lab. I'll be there.
You'll be there.
I'll probably
But you'll be there.
well, I'll be there. Nobody's helping.
So who you are and what are you doing?
We're physical chemistry students having our minds tortured.
That's good. So what about predicting future? How do we do it? What's the main mechanism for developing wave function forward in time?
Time-dependent Schrodinger equation.
Yes, it is an equation, but if you how do you construct the solution of the Schrodinger equation? Time-dependent. What is time-dependent in the time-dependent solution of time-dependent Schrodinger equation?
Phase accumulation.
Yes, yes. Good. Much better this time. So each eigenstate from time E-independent Schrodinger equation, if it is plugged into time D-dependent Schrodinger equation, starts to accumulate phase. But phase accumulates according to what's the pace of accumulating phase for an eigenstate?
The eigenvalue.
Yes. So where does eigenvalue come to?
The time independent.
It's come from both correct, but not what I was saying.
Okay.
So eigenenergies come from time-independent Schrodinger equation. Yes, in order to solve time-dependent Schrodinger equation, you need to specify initial condition. Right? That's very true. But this E sub some number, how does it enter into the solution? How does it enter into accumulation of phase?
Are you saying like sine x times 2 sine x times 2 times cosine?
This is maybe correct, but it is very narrow to our specific problem. But there is a general way to predict future. Like each eigenstate accumulates phase as exponential to the power of the eigenvalue corresponding to this eigenstate. Make sense? So this energy comes into the power of exponential, of imaginary exponential. And then the rest is just dirty work to put in coefficients and add them together. So, and what is our narrow application that we are working on? Yes, electron in a box. One dimensional. No other electron, just okay. And why are you curious about time-dependent Schrodinger equation? Why we are not happy with time-independent one?
The time-dependent allows us to predict the future.
Yes, but isn't future boring?
Expectation value changes over time.
Yes, they may change over time. In which circumstances? Are they always
between states?
Yes, yes, yes. So if the initial condition is not either one of the eigenstates, but it is a superposition of several eigenstates. So in this case, we do need to solve time-dependent Schrodinger equation. Okay, and we are looking for probably simplest possible initial condition, simplest possible example that illustrate this concept. So we are here, and today the focus on electron in a box is combined in our class of 3 sections: time-independent, time-dependent, and multi-dimensional boxes. Today we will finish time-dependent, and on Wednesday Wednesday and Friday probably at least 2 meetings for multi-dimensional boxes. The home portrait R2. I'll try to type in a better recognizable thing, and all materials which are needed to complete it successfully will be provided on Wednesday during the lecture, and all codes will be practiced collectively together during the lab. So basically, this homework is like a lab report of what we will be doing on Wednesday. So here is the access of different methods. In order to make your life harder, of course, I'm trying to pull out of textbooks more and more complicated methods. No, that's not true. It's done for better weapon against different monster in the computer game. So for some problems, some methods are more efficient. And here are the models. So we are done with free space. Now we do one-dimensional box. We are done with time-dependent Schrödinger equation, partially done with time-dependent Schrödinger equation. And last time we met, you noticed that we were setting up expansion coefficients in pairs, not just as expansion coefficient in front of eigenstate, but pairs, right? Product of C sub 1, C sub 1 star. And this combination, this product of expansion coefficients is just a comfortable notation to solve time-dependent problems, and it has its own name, which is
Infinity matrix.
yes. Right. So we are exciting particle in the box from ground to first excited, not completed by 50%. And we did agree, at least no one was objecting, or no one was caring, that if predicting future for wave function is easy. We just take solutions of time d independent Schrödinger equation, plug in eigen functions as factors, eigenvalues into power of exponential, and multiply everything by expansion coefficients corresponding to initial condition. Done. But it is not very helpful for our major goal of predicting future, in a sense, outcome of a measurement. Right? In your successful homework, you predicted the observable average position of the electron, right? You did. It was oscillating stuff because it was bouncing for some time. And sometimes, and sometimes in the halfway towards predicting observables, it is really reasonable to analyze probability distribution. Probability distribution itself is also not very useful, but it is halfway between wave function and observables, and looking at it sometimes initiates intuition and helps to understand what is going on. So the probability distribution can be combined as a summation of factors responsible for distribution in space, which we here are again states, right, again functions, and the dependence on time, where this coefficient often referred to as density matrix, and it is first coefficient corresponding to initial condition, second with conjugation, and then the accumulation of phase from both I and j expansion coefficients are multiplied. And since accumulation of phase is proportional to the eigen energy of one state and another one, and here we do have star, when we project it onto the time-dependent factor, we do get subtraction of eigen energies. Right? So how does the thing develops in time if the indices I and j coincide? I see in your eyes that you know the answer, but you do not have the right words to tell. So if these indices are equivalent, then these two energies are equal, and we have exponential to the power 0. It should be equal what? 1. So how does density matrix, diagonal element of density matrix evolves in time? It doesn't change in time. It changes in time in a trivial way. Right? Whew. And you already, I was asking myself after the meetings, what freezes the class and stops interactions? I found the bad words that makes everyone to feel better. As you remember from previous meeting, I don't want to remember anything. I don't know if that's true, but it seems like anytime I'm trying to refer to previous meeting, contact is a little bit worse. So, as you remember from the previous meetings, the energies that we plug here are proportional to the square. We do not need it right now, but later on, maybe. What else? So let's practice. Okay, we are practicing this protocol for probability distribution for a specific initial condition. I will use it just. So we have only superposition of first and second, and for simplicity we put the expansion coefficients 1 over square root of 2, right? Because if you make square of 1 over square root of 2, you will have 1/2, 50%. And then we can plug in this prescription with this initial condition. We already, well, it is assumed that we remember from previous lectures how this eigenfunctions and how this eigenenergies look like. So if we plug things in, and it is about where we stopped, there are 4 terms, right? So 1, 1, 2, 2, 1, 2, and 2, 1. So for those where indices coincide, the time dependence doesn't change in time. It's e to the power 0, trivial dependence. This 1/2 is inherited from the initial condition, right? Because it was 1 over square root of 2 in when we spoke about wave function. But if we speak about probability distribution, it is 1 over square root 2 squared. So it's 50% here, 50% there. And for the cross terms, we do have subtraction of first and second energy in the with the opposite order. Or we can write always second minus first with once minus sign, another time with plus sign. So done with time dependent part. And for space distribution, I'm skipping it here, but we always need to keep this square root of L, the normalization factor. Right now, our intuitive qualitative analysis will not depend on the normalization factor, but generally we should keep and try it everywhere. I know how to shorten our writing. We can just put here square root of L times probability distribution, so that we don't subtracted here. Now, here we have sine function with 1 maximum between 0 and end of the box, and because it is half cycle. And here we have the complete cycle with 1 minimum, 1 maximum, and we have them squared. But in the cross terms, we have their products, right? What are we doing here? What are we going to do if you already completed your lab and homework and you know the answer? Where do we invest time and what is the expected benefit? Is it again another exercise to torture young minds, or maybe there is some benefit? What do you think? Well, I do have an idea. You may agree or disagree. Suppose that suddenly there is a power outage, and we do not have MATLAB, and we need to resolve it once again with pen and paper. And then we can have an idea how to solve it. Okay? How to do the same oscillating wave packet that bounces back just by a pen and paper. And sometimes it helps to develop an intuition and practical skills for next problems. So what we are going to do is to get the same answer, hopefully, as by computer, but by pen and paper. Okay, we already discussed it. So let's look on second two terms. I hope you're not bothered with these marks. Anyone wants me to go back where this mark is not here? Then, okay. So if we look on space dependence contributing to probability distribution and coming from off diagonal terms in last two lines, you identify that this sine pi and this and sine 2 pi is the same as here. They just swap the order because the wave function doesn't, for the particle in the box as we found it, it doesn't have the imaginary component, right? So we can put this product of sines out of brackets. And inside the brackets, then we will have summation of two imaginary exponentials. Sometimes long expressions freeze the thought. So we can put delta E. So in the brackets, I'm going to reproduce last two lines. Okay. Sine pi x squared, sine 2 pi x squared, and in the you can put 1/2 E minus delta E h bar t plus E plus pi delta E h bar t. So, which thoughts visit you when you look on a blackboard? Do not do not tell to do something bad to the instructor. I mean mathematical thoughts.
My last one.
Yes. So what will be the Euler equation for this construction? There are only two if you roughly remember, there could be two outcomes.
Is it going to be 2 cosine E2 minus E1 over H bar times T?
Everyone agrees? Right? So, and if there are 2 cosines, you cancel factor 1 to here and there. So cosine of this delta E H bar T. I have forgotten that I was typing. Cosine. Cosine. E. So what should I do if I'm playing that I'm a little robot or computer that tries to solve this problem instead of MATLAB and PC desktop? Or what would you do if you need to? Remember in your lab and homework, you got this bouncing force and back distribution. It is here, but how is there a way to reproduce this bouncing force and back distribution out of this equation? How will you plot it? Do you identify balancing function in this set of equations or not quite? I do not identify it in this way as well, but we can do it relatively easy. So we need to replot this function of position at different time steps, at different values of time. And we already know that cosine is not a very complicated function. We know that it performs regular oscillations, repeats the same pattern. So probably to get an intuitive understanding of what is going on, it would be sufficient to look at the values of time which are most important for the cosine. Maybe when time equals 0, when it is in the most negative phase, and maybe when it is 0. So the most negative phase will be when the argument of cosine equals pi. But what will be the time if we set up that pi equals delta E H bar T? So time will be pi H bar by delta E, right? It will be this instant of time. And the instant of time here will be twice as small. T equals pi H bar divided by 2 delta. Is it clear or is it boring or it is both clear and boring? So if the argument of cosine equals pi, right, we just set up pi equals whatever was argument of cosine and solve for time. And we do see an interesting, well, it's very trivial but interesting observation that time steps, units of time, can be expressed as inverse of energy offset between levels. So there is some internal connection between energy offset between levels and time steps. How many who in the class? 1, 2, 3, 4, 5, 6, 7, 8. I will be number 9. Let me invite you to come up to the blackboard and fill the table one by one. Kevin, you'll be second. I will be first. So, if you are taking notes, you'll have the whole expression of things. So we will explore these elements of density metrics which define time propagation at most critical instance of time. So we know that the first one doesn't develop in time. And at time 0, it will be just C1 absolute value squared, right? Or just use a finger.
Okay.
Perfect. It will be quick. Yeah, you did it smartly. You selected the simple one. Prepare. Oh, yes, yes, you see, it's good to be at the beginning of the learning. Which one you prefer to? Oh, you prefer not to do it?
Yeah. I don't know which.
Like, what's the time dependence for this one? Is there any time dependence, or I just trivial?
Don't remember.
No. Take help from the class.
It's trivial. Trivial.
So if you try to put something here, we would change compared to time equals 0. So at time equals 0,
Yeah.
it was 1/2.
Yep.
Would it be something different at this time?
No.
So just plug in 1/2.
It's good too.
Great, yeah, thank you. So, prepare. You chosen most. Yes,
Alright.
great. It was most untrivial cell here. Ben? Yes, excellent. The rest of the class, you guys are safe. Okay. Yes, correct.
Duh. This one.
You prepare.
I don't know. I think you got a hard one.
No.
Wrong.
Many thanks. So the class performs really great. Everyone did correctly. And first, I do not know why you need computers in MATLAB. You can do things yourself. Second, sometimes the class doesn't feel enthusiastic to support discussion, but I do not see a reason for it because you're understanding stuff and performing really well. Okay, so it was a class of previous year. You did it quicker. So what do we do next? If you want to get this bouncing distribution, we are going to plug this set of numbers 1/2, 1/2, 1, 1/2, 1/2, 0, 1/2, 1/2, minus 1, as a factors in front of this trigonometric space distribution function. So we need to plot 3 times. And of course, computer was doing it with much finer grid, but if you look on the most typical critical points, we'll project with our mind how it looks in between. So we are taking this blocks of 3 numbers and plug them into expression for probability distribution. So for, at time 0, we have wave function of ground state, wave function of excited state with coefficients 1/2, right? We do not change. And then we have factor 1 in front of this sine pi x, sine 2 pi x. For the another specific time, we keep the same 1/2 sine square pi x plus 1/2 sine square 2 pi x plus 0. Probably it will be the simplest one. And then we have again 1/2 sine square pi x square sine square 2 pi x square minus 1 sine plus pi x square sine 2 pi x. So if you plot these 3 functions, it will be sufficient to get an understanding of what is going on. And you already know from your homework that it will be bouncing stuff with like a 2-hump camel where height of humps change with time. Yeah, here's the same thing, just in better calibration. So suppose we are taking the first of them. And we do want to plot. So it is very senseless activity today because it is very unlikely that power will drop and you have no computers. But just in case, sometimes you can sketch and develop educated guess how solution may look like before you write or before you run the code. So what you are invited to do is to draw this function. Approximately, we will not measure how high the function is, but just approximately. So how would you do it? Any ideas? Like if you have an hopefully not in this class, but in some other class, if you have an exam or quiz and you just have a function, you are not allowed to use cell phones and calculators, and you need to plot it.
Like assign it critical values.
Yes. What are the critical values?
When the function
Yeah.
when the function of sine is equal to like either 0 or pi over 2 for the argument of sine.
Yes, it is one thing. But this is again specific for this problem. Generally, if you have a function with equation and you need to plot it, what do you do?
Or like if derivative is equal to 0.
Yes, excellent idea. Another idea? Explore where function itself is equal to 0. Right? So it will be just points where it crosses x-axis, if any. So derivatives, we will not practice it here, but it is very correct, where it is equal to 0. And another things, one can probably represent a function as a summation or product of much simpler functions that we know how to do. So can we identify something simple in this expression. Can you factorize it?
No.
Well, my ideas do not count because I did it before. So you see sine pi x here. You see sine pi x there. It would be a good candidate to take out of brackets, right? Do we have sine of pi x in this expression? How come? Here the argument is pi times x. Here it is also pi times x, but here is 2 pi times x. If my passionate desire is to take sine of pi x over 2l out of brackets, how do I identify this argument of a single argument in here? Like sine 2 alpha equals 2. It's the one equation I remember from high school. I want to believe everyone does so. Sine of a double argument.
Sine alpha, cosine alpha. Oh, no.
Correct.
Oh.
Michael Odegaard. Thank you for the help. So this sine square can be interpreted as square of 2 sine pi x l cosine pi x over l. And then in each of the 3 terms, we do have sine square pi x over l here. And we can open this once again. So in each term, we will identify the sine square pi x over l. So can I flip to the blank slide to write something? So I'm going to progress to do things at time equals 0. So our p will be half sine pi x over l squared. Second term will be 2 sine pi x over l sine pi x over l squared plus 1 times sine pi x over l times sine. I will replace sine pi x over l times cosine pi x over l. Good. So there was a sign of a doubled argument, but I opened it according to the equation suggested by Michael. So I identified it 2 times. And I'm going to swap the power and see. So we do see common factor. Sine square of the pi x over l. And here I see it from here and there. So each of these 3 terms contains the same common factor that again put up front. So sine square pi x over l, and then we need to identify what is left inside. So 1/2 plus 1 cosine square pi x over l plus 2 cosine by x over L. So we reduced our function that we need to plot into the product of sine and the summation of constant and cosines.
Shouldn't there, in the second term inside the bracket, shouldn't there be 2 times cosine squared?
But there was 1/2.
But you have a 2 in front of the sign that should also be squared, correct?
Or
So right in front of the sign, there's a 2 inside the square, so shouldn't 2 squared be 4?
direct my finger.
Just point straight into the board.
Here?
Other way.
Here?
No. Inside the bracket, go inside the brackets, the first brackets. Up top.
Out.
Here or there?
Where
Go
the
and
shadow is.
Go and show.
Where the shadow is.
Right here. This 2 isn't it inside the square?
Yes, yes, thank you so much. Ah. Now that's plus a point. Excellent. That's correct. That's correct. So, then it will be 2 here. Super. So, what I'm suggesting to how to process is to plot the sine square and then plot what is inside the bracket. Because if the products are really easy to visualize, and we already know how to plot sine square, so we need to deal only with the thing inside the bracket. So, and when plotting the function inside of the brackets, probably we can plot 1/2 plus cosine plus 2 cosine, and then add this stuff. Splitting it this way is reasonable because cosine square will be symmetric in respect to the middle of the box. And this will be antisymmetric, so it will disbalance the humps. So we have sine square x over L one function. Another function will be 1/2 plus 2 cosine square pi x over L. And another one will be cosine pi x. So I'm going to focus on this first. So everything will be, I will need to offset the origin by 1/2, right? Because adding something to the function is just shift. Then cosine square pi x will be maximum at 0 and will be -1 at when x equals L, right? But if we square it, it will be always positive. Makes sense, or should I draw it in more details?
Okay. Shouldn't it be at 5/2 up there if you shifted it up one by 1/2?
Yes, correct. 5/2, yes. You are accumulating points. Well, do I need to go over details of how this comes up, or is fine this way? Yes or no? No. You want to believe it, or you see how it develops. Good. So we have this function, which is symmetric. Now I will just draw it on different axes. The 2 cosine by x over L will be plus and minus. Plus 2, minus 2. So if we add together these two functions, then at left edge, the height of the hump will become higher, up to 4 plus 1/2. And at the right edge, it will be how much?
1.
No. It will be 2 plus 1/2 minus 2.
1/2.
Something is wrong with coefficients. It should be, the factor here should be different. So probably the factor here is 4, but I'll put question mark and figure it out and send in the notes after the meeting. So after summation, it likely will cross the probably everything is good. 1/2. And when we multiply this function by sine squared by x, it will become zeros at the edges. There is a better way to do it. So I cannot give it up, and we don't have more time, so I need to dedicate part of our next meeting to this. But if we carefully process it, we need to go to conclusions, otherwise it will be too long. So if you carefully process it, we will get the displaced humps. So in at time 0, it will be shifted towards left. Time h bar over delta e times pi, it will be shifted to the right, and in the middle, it will be symmetric. And it is what we are getting. What we are getting if you write your method code. So you see the critical values at beginning, at the half period and quarter period are humps shifted to the left and right. So about first 10 minutes of our next meeting, I will give you certified details how we arrived to it. And here is my favorite slide. So see you on Wednesday. There is no reason to invest time into any homework because preliminary steps towards homework will be given on Wednesday.